All right, so we're gonna get started now. It's 4:38. Can you guys hear me fine?
Yeah.
All right. So welcome. Thank you everybody for trudging through the rain for this. I appreciate it for coming out. This is the Intro to Shader Programming workshop. We're gonna be covering introductory shader concepts, syntax, and examples, and like live coding. So again, we're gonna be using shadertoy.com. It's really easy to start up. All you need is a web browser. Google, Chrome, or Firefox are good. What's up? It's being recorded. Yeah. All right, so let's get started. What is a shader? So basically all that a shader is, it's a GPU program that runs on GPU hardware. That's like the basis of what it is. Why is this different than the regular programs we use with our favorite languages? So unlike traditional CPU code, shaders have like special constraints that make programming them like kind of weird and different from traditional code. So what do people use shaders for before we get into them? So when people think of shaders, they typically think of like vertex or fragment shaders in the like rendering pipeline context. So vertex shaders in like computer graphics and the rendering pipeline, they perform operations on vertex and geometry data of like 3D models. So like your cow 3D model or something. And fragment shaders, they take that data usually, or usually the vertex shaders are their output is passed into the fragment shader's input, and they're used to compute pixel or color data for each pixel or fragment. There's more that you can go into there with like how they define fragments, but they're basically per pixel. And compu shaders are kind of a more generalized thing, and they're used to just compute other things. So kind of anything you could think of. So why shaders? Like why use a shader when traditional code works perfectly fine? So this is an example from the Book of Shaders. It's a great like introductory resource to like start getting into like shader programming, like more on the like shader art side of it. But so I'm gonna use this analogy here. Again, Book of Shaders, highly recommend it. So we see here we have the CPU and GPU like pictures here. So imagine that your CPU is just a big industrial pipe, and the tasks that the CPU handles are things that pass through the pipe. So like your product or whatever. So in this analogy, a pipe is what we would call a thread. So like your CPU, you've probably heard that they have threads or whatever. This is a thread basically. Well, a large pipe is great for making complex things, but they make one thing at a time. So each product needs to wait for the other one to be done before they can be made. This is where the GPU comes in. So as you can see, we have our large pipe on the top. The GPU has all these tiny pipes. So basically, these tiny pipes are threads. They can compute tiny tasks in parallel. So we're not going to go too much into depth of like how GPUs work. I don't know that much, honestly. Like I only know like a surface level of how they really work down. But this is the core concept of how GPUs work. So from like a rendering point of view, to like put things into scale, and like why we would use shaders. Your screen, let's say it's like 1920 by 1080 screen, like resolution. That's roughly 2 million, a little bit more than 2 million pixels that we need to calculate. So we don't want to have to do that. We don't want to wait for each pixel to be done before we get on to the next one. And they're relatively simple like processes for each pixel to get color. So we can use the GPU to calculate the color for each pixel at the same time. So that is why we might use shaders. But again, the reason that their shaders are like shader programs are kind of weird is that there's these limitations here. So in our analogy that we had in the previous slide, each thread, each pipe was a separate pipe. So you can't read data from other pipes at the same time, and you can't see what was happening in a previous state. So these properties are basically summed up into like blind and memoryless programs. So we'll see more examples of how this works, but these are just like kind of the base concepts to keep in mind, is that you can't see the memory of a state in previous moment, and each thread is independent from one another. All right, so this is a simple example. This is the one that ShaderToy gives us. Oh no, actually, this is not the one that ShaderToy gives us by default. I'll pull it up. So this is. Oh, let me make this bigger. I think it's there. Is that big enough? That should be big enough, right? Can you guys see that? All right, cool. So let me go back to the slides first. We'll cover the okay, we'll cover the bullet points first. So some general like things to notice here. So first of all, ShaderToy uses GLSL. That's the language that we're going to be. That's a shading language that we're going to be working in today. When you're writing shader programs, you have to talk to the CPU sometimes. Not the shader programs don't talk to the CPU, but the CPU talks to the shader programs and passes them stuff. Well, actually, they work both ways, but we're not going to be worried too much about that. ShaderToy kind of handles a lot of that for us, which is really nice. But so this is GLSL code. It's a C-like language. There's a single like main function that returns a color at the end. This is a fragment shader. We have built-in variables like frag color, frag chord, eye resolution, etc. Those are what ShaderToy defines, but they can be called whatever in like other programs. So we have types that are special. So we have things like vec2, vec3, and vec4. You can kind of see those there. They're vectors. So if you guys don't know what vectors are, they're simply just a container of scalar values, which are just like your floats or your ints or whatever. I guess the door's still locked. So these vectors are nice because a lot of the stuff we're dealing with is not just single scalar values. So for example, you can see in this code, UV, that's a vec2. It defines, it's like X and Y coordinates for your screen that are normalized. Vec3, color. So vectors can store whatever. If you guys have heard of RGB, that's like that's one way we store pixel data, like for color. So that's stored in a vec3 here. And then the reason we're passing a vec4 is because that last value is alpha. So that's transparency. All right, so we'll look at a at the my playground here. So another thing that's cool that you can do with these vector components or these types are how you access them. So you can see here, I'll actually, you guys should have this at least this top thing. So you guys should also have this vec3 color thing here, variable here. So right here we're instantiating a new vec3 by putting the parentheses around or after we say vec3. And you can see we're passing in uv.xy. That's interpreted as a vec2, but to complete the vec3, we need a third value. And I'm just putting in 0 because I don't care. And color is what we're assigning that to. So what this is doing and what our output is showing is the UV components as colors. So I think I could just use my pointer. Yeah. So you can see on this bottom left here, it's black. So that's a UV chord of 0, 0. So the bottom left of our screen right now is set to 0, 0. And you can see this bottom right here is red. So RGB, right? We have red is 1, green is 0, and yellow is 0. Right, and blue is 0. There's actually no blue at all. So we'll just do red, green for now. We can see, so that's uv.x. That's uv.x equals 1. So that, and then same thing up here, it's green. And then we see a little bit of yellow here. That's because we have both red and green, not 0. So how are we getting these UV coordinates? yeah, I guess I can't really see it, but so we're taking in our frag chord. Frag chord, it's this variable that the CPU is actually passing us, and it gives us the coordinate position in screen space of a certain like fragment or pixel. Well, I'll call them pixels. Uh, and what I mean by screen space is the screen space is not a normalized space. So this bottom left is 0, 0 regardless of screen space or what we're going to define as UV space. But screen space, that point right there is 0, 0. But the top right point, does anybody want to guess what that value might be?
1, 1.
So screen space. So in screen space. So in UV space, it is 1, 1. And we're gonna something like that. So it'll be your resolution. So you can see here we're taking and I guess I should explain what this dividing is doing. So there's no you can't divide vectors really. You can only divide them component wise. There's no like actual vector division. But this divide symbol here is dividing each component of the vector by the other vector. So we have frag chord xy, I resolution.xy. So I resolution is our given screen resolution. So now the max value of frag chord is whatever the resolution is, and we're dividing that by whatever the resolution is. So now we're in the 0 to 1 range. And it's really important because a lot of shader programming relies on kind of like manipulating what your like kind of ranges are, what your space is. So you'll see that later on, but so it's always good to know what your range is. So you see, I even commented there, we're in that range of 0 to 1. Also, so accessing vectors, we can see .xy, but we can also do this thing called swizzling. It's a fun word. So you can access these vectors. You can also, there's other like accessor things we can use. RG, so for RGB, we can say RG, and I just ran it there. Alt Enter should run it for you instead of pressing the play button. That's the same thing as XY. I think ST as well. That's like another weird way of that they've decided to call it. But so swizzling though, we can reorder these things. And oh, I put a 0 there. We can reorder the way we're accessing this. So now this uv.yx is returning a vec2 that is the uv.xy's coordinates or components swapped. So can anybody take a guess of what the visual is going to look like after this? Yeah, so on the diagonal, where it's like the inverse. So where the green was, the red will be, and you can see it. So that's some basics. Let me go back to the slides. Oh, cool. All right, so these are some useful GLSL functions. I won't spend too much on the definitions because I have some like we'll go through like how they work. But length gives you the scalar length of any vector you pass it in, or scalar. Well, actually, no, you can't pass scalars, or maybe you can. I don't know. But any vector you get it, it'll give you the length. Step is basically, you can read it there, but it's returns 0 or 1. So again, gives us that 0 to 1 range, which is super nice, based on what your edge is. Mix is a linear interpolation between x and y using a as the weight. So a usually want to keep between a 0 to 1 range as well for things to work, but say you pass in 1 for a, mix x, y, a, that function will return the value of y. And if we set a to 0, it'll return x. And if we set it anywhere in between, it'll interpolate between x and y to that value. So like 50% basically is 0.5 if you pass 0.5 into a. That's like 50% between. And then fract, we're not going to, or yeah, we'll use it, but we're not going to use it for the example. But it's the fractional part of x. So anyways. Smooth step, similar to step, but it does a cool thing where instead of immediately returning 0 or 1, you can define two like edges, and then it'll between those, so it'll return 0 or 1 on the outside of those edges, but between those edges it'll return a smoothly interpolated, so different than linear interpolated, but smoothly interpolated value between those two edges. So you can kind of see the graph there. That's sort of how it'll look. And sine and cosine. Okay, I'm gonna go do these. We're gonna look at these. So okay. So I'm going to. It's really hard to. It's like really delayed. All right, so we're gonna look at some. I'm gonna put them in here. So we're gonna look at how these functions work. We're gonna use UV, so our UV coords as input. So for length, let's just see what happens. Did I spell that right? All right, so we're passing in our length, or we're passing in our UV for length. So can anyone guess what this does? What it will look like? Or you could just like type it on your computer. All right, well, I'll show you. It looks like that. So you can see on this bottom left where UV is 0, 0, it's returning 0. It's black. And oh, I should explain this. So we're passing in a scalar into a vec3. That basically returns a vec3 where each component is that single value. So all the components are the same. So that's why it's black and white. It's not, there's no colors. But yeah, you can see that as UV xy gets basically bigger, we have more white because the length from 0 is the length of the vector. Because so this is like a bit of more of like how vectors work, but vectors are in relation, like or direction vectors are in relation to like an origin point. So the length from 0 to like that point up there in the top right is of greater than 1 value or greater than 0 value. All right, so that's length, and then let's look at step. So step, we pass in first the edge, and then the, what is that thing over there? Okay. So we pass in the edge that we want to compare, and then our input. And actually, I just realized we can't, it takes in only a scalar. So we'll do x for now. So we're not taking into account the y coordinates, and you'll see how that looks. Pretty, you know, predictable. So, you know, if we lower this value, we can see that it'll shift more one way. And so yeah, that's how step works. We get a 0 or 1 value based on our edge. All right, next function we're going to look at is mix. So this function, or this example will be like less intuitive, but you'll see actually more intuitive one later. But so we're going to mix between the values 1 and 0 based on our UV. So remember, UV.x from left to right is going 0 to 1, but we're mixing, so a 0 value will return, in that mix function, will return 1. So you'll see that it is going from 1 to 0, left to right. So if we just passed in uv.x, it would be the opposite of this. It would be flipped. So yeah, it can be very useful. We'll see a cooler example later. Yeah, I'll show you the fract one. That's cool. So again, fract, it's a little less like intuitive of how we would use it just by reading it until you like see. So we'll start with this. You'll see that it'll actually be just like how you passing in uv.x is. And the reason is that uv.x doesn't get past 1, and it returns the fractional value of it. So you never like get that repeating sense because you're never actually like changing the value of uv.x. But if we multiply this by some value, any value, you'll see that it kind of repeats. It's pretty cool. So you get these repeating things. So you could do something over and over again if you knew what you were doing, if you had an idea in mind. So that's how that could be useful. And then smooth step, that's a fun one. So if you guys remember, our step function returned, or not returned, but it gave us output that was either white or black. Now here, I'm passing in 0.4 and 0.6 as our edge 0 and edge 1. So that means values less than 0.4 will be 0, and values greater than 0.6 will be 1, and values in between are smoothly interpolated between 0 and 1. So you'll see we get, instead of that harsh line, we get a little bit of a smooth gradient, I guess you could say. And we'll see that also come into play later. Okay, so that's enough of that. That's kind of how the functions work. So keep going. Shaping functions, I won't cover this too much, but it's cool to know. Also wanted to mention a really cool guy that is basically like really cool in shader programming but and mathematical art. But shaping functions are nice. If you have some sort of input that's maybe like on a like this like kind of like changes at a linear scale between like some values, you can shape it. So you can apply cool functions to it. Let me, it's fine. You guys can check this out later. But if you search up Inigo Quiles, he has a whole website, and he has so many articles. They're really good. I haven't read them all, obviously, but he has one called Functions. So just search it, just find functions. It'll be there. And there's a lot of cool functions that he's written for us in GLSL that we could just use. Give it an input. It'll give us some shaped output. So that's that. Let's try a simple shader together. Wait, don't. Actually, do I want to do this one? Yeah, let's do this one. We have time. Okay. So, all right. So we're gonna do a cool shader. Go back to my playground. I'm gonna delete. Everything up until where we define or where we define UV, and also I'm even removing that stuff. So right now, it'll actually error, but all right. So we had that cool UV thing that like that range that was 0 to 1, but that kind of like, I don't know. It was, it's like uh, going in that direction. So like our 0, 0 value is in the bottom left, but when we look at like a graph, the origin's usually in the center. So what if we wanted to center our UV? So one thing we can do is, I'll do this in steps, but later I'll condense it. But first we define UV as just our screen coordinates. So that's 0, 0 to whatever our resolution is. So the first thing I'm going to do is multiply that by 2. So that's going to give us a range of 0, 0 to 2 times the resolution. Next thing we'll do is subtract that larger range by the resolution for both coordinates. So this is, everything here is component-wise, like calculations. So there's nothing else crazy going on. There's no dot products, no cross products or anything like that. It's all component math, I guess. So now we've you know what? Let me show you guys actually. I can just pass in, or I'll just make a. I'm gonna define color here. Yeah, that works. Okay. So actually, we can just backtrack too if you guys want to see how that looks. Oh, that's weird. So yeah, first we have all yellow because we're outside of our range. we can't see anything. But then we subtract it, we offset it, and look, it's kind of in the center now. And this would be fine, except that, and you'll see later if you were to do this, we haven't normalized yet. So this is still in the 0. So now, so basically we shifted everything over, but it's still in the 0 to resolutions range. So now we just want to divide by iResolution. Now, however, you'll notice that I'm dividing by iResolution.y. So I'm dividing both of the UV chord components by y only. So if we divide both by the height of the screen, we get square coordinates, sort of. So you won't. Did I mess something up? Well, we can do. Well, anyways, the idea is that there might be something with like how I'm separating it up that it might be incorrect, but you'll see in the next example, it'll get fixed. But the idea is that we bring it down to the 0 to 1 range again. Okay, so next thing, the coordinates don't matter that much for it, but yeah, actually, let me check something out. Yeah, I must have missed. Well, anyways, maybe I'm just looking at it weird from this angle. It doesn't matter. So we're gonna look at how we can sort of like change colors. Pretty cool. So I'm going to just define, just define that there. All right, so I'm gonna come up with this t value. Now, this t value is gonna be an interpolator, interpolation value, whatever you want to call it. So nothing will change yet, but this is good. So iTime is a global variable that we have that just gives us the time. It's actually, well, it's really tiny, but there's a time value you can see like on the screen. It's that. We're gonna pass that into sine. We're not gonna worry about 2 pi for like the correct phase and whatever. Like we don't care because it doesn't rely on that. And then we're gonna absolute value that. So what that looks like is if you know your sine function, it just looks like that, but it's only positive values. So it doesn't cut it off, but it just like bounces it up, I guess. But I'm sure you guys have seen how sine looks. And then, all right, so we have this value. It's not useful yet, but now I know we have this color value, but I'm going to come up with another color value or variable, and these values I'm putting in are just it's just a color. These are representing a color. T. And did I type mix? Yeah. So make sure everything's right. So right now it'll be black. And then what we did there for our value C is we're using T as our interpolation value. It's a value between 0 and 1 because sine returns a max value of 1. And we absolutely valued it, so it can't go lower than 0. So we have a 0 to 1 value from T, and we're passing T into our interpolation, our mix thing, and we're going to mix between these two colors. So that's red. Oh, I put 2 ones. We'll do that. It's red and then some combination of green and blue, which I don't remember off the top of my head what that is, but if anyone knows colors. But and then we're just going to assign color to that. And now you'll see it is blue. This is because of this. We're gonna just, actually doesn't matter for this. Or I guess it does. So I guess this wasn't the greatest example of splitting up the things like that, but I will quickly write what the condensed version looks like and what you'll commonly see for the UV coordinates. I think it's like an order of operations thing that I messed up. You will see a mix between hold on. Between the two colors. I can't even tell what my cursor is. Boom. What did I do wrong? Oh, right. Oh no, that should be right. Okay. We will copy my code. I feel like I'm cheating here, but this is, okay, so you'll see I have even comments here, so this might even be better. But yeah, I don't think I did anything differently. It's weird. Anyways, so there's some stuff here. Don't worry too much, but it is basically the same code as you can see. So we have T, that's our absolute value, and then we have C, that's our mixed color, and then we're just passing that into the, and you'll see that because we're, oh, I'm so dumb. It's because we didn't press play. That's why. It's because we didn't press play. It wasn't me, guys. So you can see that it shifts between colors because we're passing in time, and time needs to be moving for things to change. All right, moving on. We spent too much time on that. All right, so that's the simple shader. All right, so next thing, sign distance fields. Pretty simple concept. So you give, so they're used to represent shapes. They take in a position at any given input in screen or anywhere, and they return a value. It's signed. So the sign of the value that you get depends if it's inside or outside the shape. So a negative value means it's inside the shape, and a positive value means it's outside of the shape. So they're very useful for defining shapes. And there's a lot of math that goes into this. Again, Inigo Quiles, he wrote out like tons. These images are from his articles. He wrote out tons of code to define these shapes, and they're crazy, and I don't understand them. But he's a crazy guy. So another shader, simple shader. We'll go quick. So I will probably just copy some of the template. So we're going to look at SDFs. All right. So we'll leave that there. And we'll just grab all of, not all of that. All right, so this should be the same thing that you guys had earlier, but you just check out how we're defining UV. So we're multiplying by 2, subtracting it by the resolution. Oh, that's what I did wrong. I subtracted by frag chord. That's what I did wrong. That would, yeah, that's incorrect. So you subtract by I resolution and then divide by it. I think that's what I did wrong. Anyways, I get those two confused. Okay, I say -1 because 0, it's centered at 0, so the left is going to be -1, but it's actually not -1. It's because it depends on your screen size actually, because we're dividing by y. So the square in the center of our, like the largest square that we can get in the center of our screen is between -1 and 1. Or sorry, oh wait, I actually misplaced that. It's -0.5 to 0.5. Yeah, sorry, that's my fault. Must have been tired saying that. Yeah, so it should be. Okay, great. I commented it. Anyways, whatever. It's not -0.5 to 1. We're gonna delete that. But it's like input delay is crazy. Okay. Anyways, so you'll see that we have black. So yeah, we're gonna do some SDFs. So the simplest SDF that we could think of, we can make is a circle. Or this is a 2D SDF. There's 3D ones too, and they're kind of defined like pretty similarly. So for our SDF, the first thing we're gonna need, and SDF, yeah. So the first thing we need is a radius for our circle, right? So that's R is our radius. And now a lot of people will return the value you get as D because you'll see later that this value is, or this sign distance function isn't the best to use directly with like other stuff. You usually have to use it and then like normalize it to a specific range. But so you'll see that length value, length function come back in. So we're gonna pass UV into length and then subtract it by R. So what this is doing is giving us the length from 0 and then subtracting it by our radius. So values that are on the line. So when length UV equals R, that's d is equal to 0. That's exactly on the line of our circle. So when length uv is greater than r, that's values outside of our circle, and then when length uv is less than r, that's negative and it's inside of our circle. And then we'll just go. So we'll set color to D, and you'll see we sort of have a circle. Yeah, it's sort of a circle. And you can see it's kind of fuzzy on the edges because we're not stepping or anything. But what if we want to make like a mask, sort of? So we could do is, I'm just gonna call this SD, and this is our like step mask, I guess you could say it. But we're just gonna pass, like, I'm just overcomplicating it to, like, I guess screw with you guys, but we're just gonna pass our distance into step with a very low value. And the reason I'm using a low value is because, remember, our line, like a value close to 0, our line is on is when d equals 0. That's like the line of our circle. So I'm getting it close to that. I guess could use 0, but I forgot to. And we have a circle. Wow. So yeah, we stepped. All right, next thing, I will show you how we can. So, something I really don't like. I don't know if you guys can see it, but those that circle is a sharp circle. Pixels are on this screen right now are either all 0 or all 1. So because of that, it ends up having jagged edges. So to kind of remove those jagged edges, what we can do is, so I'm kind of going to overwrite code here. So the SD function, or the SD value, we're not even going to be using anymore. That was just an example. But we're going to use smooth step because it's smooth. This is kind of the reason I use the 0.01 value. So we're going to go between 0.01 and 0.1. And I have to pass it in. And you can see we sort of have a blurry circle on the edges now. And we can close that value even more to get a more defined edge, but like there's still some like 0.5, 0, point whatever values, not just strictly 0 or 1. Okay, that's a circle. So yeah, look, we can make shapes now. That's pretty cool. All right, so how do we kind of like combine this all together? Let me pull up that. So yeah, how do we combine this all together? That's the code. So yeah, you guys can create a new one or the same one you guys are on. We're gonna look at a challenge. We're gonna make sort of like a radar thing, ping thingy, sort of, using all the tools we currently have. So yeah, let's get to it. So this is our target output. So we're gonna go back to this. All right, so we want things. So first of all, we saw that the radar was kind of centered in the middle, just like our circle is here right now. So we want to keep the UV chords the same. First thing we want to do is, I'm just going to delete all of this except for the frag color at the bottom. Okay, what's up? Oh, sorry, you go first.
Oh, sorry.
You're good.
In your vector 2 UV, what is it at the end of the line? You divide it by I resolution dot what?
Y.
Dot Y, that's it.
Yeah, you can do either, but dot Y gives us a square area because your screen. So if you're dividing both by the same, your screen is not square, right? Well, it's not always square. I mean, if you have a square screen, that's kind of weird. But dividing it by the same value, or height in this case, if you've ever heard of aspect ratio, that's the ratio between your square coordinates, so your to like your screen resolution, kind of. It just makes things nicer. I can actually show you guys what this looks. Well, I deleted all the code, but I can show you later what it looks like if we don't divide by, if we divide by XY. So yeah, now we have well, nothing because we have no color. We'll put color here. So now we have black. So the first thing we're going to do is so we saw it was kind of like a circle, kind of like it was like rings of a circle, right? Actually, can anybody guess what we might be using to like make this? Like what component, like what tools we need to like give this like radar thing? This is it, by the way. What's up? You, yeah. Fract. That's actually a good guess. And you might be able to use it if you like use polar coordinates or something, but we're not going to do that. So close, but that's actually the one function we're not going to use. Time, right? Because it's moving. Okay, yeah, well, we're gonna see. So, see. Okay. So the first thing we want, it's kind of a circular shape. So we're gonna use an SDF. Now you'll notice this isn't really a true SDF. It's actually kind of just the distance from the center. The reason I'm doing that is because we don't really need a circle. We just need the distance from the center. So I'm just going to, just to show you guys what it looks like. You have to say vec3d because that's a scalar. So, oh, what? There you go. So we have this. So this is showing us the distance from the center of our UV from 0, which is center at the center of a screen. So yeah, so we're gonna start with there. Start there. So the first thing we want to do is to play with these values. These values are bounded between 0 and like, I mean, whatever our screen size is, but pretty much infinity. Like, because it depends on UV, right? But they're not 0 to 1, which, or any normalized values, length or range. So we don't like that. So we're going to normalize it. So we're going to create a mask. This mask is going to be used later for our color. That's float, not float. So this mask, we're going to, it's kind of tricky until you think about what sign is doing. But we want our mask to be normalized, and sign is normalized. Sign returns normalized values. It's great. So what we're going to do is pass in our distance. And I guess if I'm going to stop erasing this. If we pass in what our mask looks like now, I guess, yeah, nothing much happens. You can kind of see the edges are maybe changed a bit. That's because the value in here, it's too big. The phase is too big. I think that's the right word. So if we multiply this, you'll see that things, oh, whoa, it's looking a lot like our thing, actually. So you'll see that we basically closed in the, I think the phase is the right word for it, but I'll have Desmos here to prove it for you guys. So you can see here, this is kind of what we did right here. So this A value is that 11 we used. It could be any value, but the higher this thing gets, the closer the, I forgot how sign works, the words you use, but the closer together it gets in layman's terms. So there's other ones there, secret. So we already have like pretty much like the biggest part. So someone said it earlier, time. Time's the next thing we need. So, oops. Yeah, so how might we, so these are basically our sine waves. Like this is what the graph was looking like. This is 1-to-1 to our graph. So how do we like, does anybody have any guesses as to how we could like shift, keyword shift this? Yeah.
Make the phase inside of the sine function dependent upon time.
Right. And how so? Multiplicatively, like, but we already multiplied 11 by distance, and that just made it closer together. So maybe, but we want to shift it. So we add or subtract. Yeah. So someone said add. We can add, and you'll see what the difference if we add or subtract it is. It just goes inside or out. But ooh, it's moved. This is basically it. Like we're extremely close. But we want colors. White's not cool. We want color. We like color. So but we have the animation part of it down. So another thing I'm gonna do, and you'll be like, why didn't you do this earlier? Because wanted to see if you guys were cautious. So what is our range here? Our range of values. Like what is the, okay, so a color values. So what is the max and the minimum value that mask, that value mask can be? -1 to 1. So, but how do we render an, so our color is bounded between 0 and 1. We can't have negative RGB. That'll just be 0. And we can't have anything greater than 1. There's no high dynamic resolution going on here. We just have 0 to 1. So we don't want tricky values like that. So we're going to like mask our mask, I guess. So we just slap an absolute value on that. That sticks it between our 0 to 1 range. And you see there were hidden lines there. That was what was going on under the x-axis on our graph. That was all those loops. Now we put it all above the x-axis. This is way more representative of what was actually what it looks like. And you can see it basically doubled our lines. So there was like invisible lines there. You could think of it like that. Next thing we're gonna do, I'll code it up first and then explain how, like, why. It's a little weird. I didn't actually think of this myself, but it's pretty cool. And I just don't want to make new variables, so I'm just gonna keep reassigning it. But so this is like a weird operation. So we're kind of doing the inverse of mask, but not 1 over mask. This other smaller value over mask. And I'll show you why we do the smaller value in a second. But this is essentially the inverse of mask times actually a big value. No, times a smaller value, sorry. But so you'll see, well, actually, I don't know if you really won't see, you won't see too much here, and it'll look better in a second. But I guess, yeah, this part is like, you don't see it until later, so I guess I'll go back to show you how this kind of works. You'll see, this is a little harder to explain, but what we're gonna do here, if you look on my example, you see how like the center, this is kind of low res, but you see how the center of the lines are more vibrant than the outside of them? It's because they're not going from black to white linearly. They're going it's like I don't even know what oh, let me go to Desmos. It's this bottom one. It's like inversely, I guess. I don't know. But you can see, and again, we can stick into that 0 to 1 range. So, well, 1's up there and 1's down here. So this is like kind of our screen here. So instead of just having it linear, we have kind of this like thing going on. But anyways, you'll see how that changes stuff. I thought it was cool, but I don't, think it's the most necessary thing, but it looks cool. And you'll see how it looks cool in a second. It looks kind of weird now, but we'll find out soon enough. So next thing we want to do is smooth step. So I'm just gonna re-sign it again. This is where things get like, things can get kind of weird. Like it's kind of weird to like understand what, like why you do things. And sometimes you just do, kind of the rule of graphics is like, if it looks good, it is good. Like you don't have to worry too much about why it looks good, just that it does look good. So you'll see now we get these like vibrant lines. So this compared to what we had before, actually, yeah, I can show you. So if I comment out that, so yeah, take a look at that, and then take a look at that. So you can see, I mean, they're a bit thicker here. You can see there's a lot more, it's more gradual, the change between the black and the white, but here it's a sharper change. And I think it just looks better. But that's, again, like, this could be defined, this could be under like shaping functions stuff we're doing here. So we're kind of shaping the thing. We had the general shape already, but we're shaping it now. So we already have, this is the entire thing, but there's no color. So the great thing here though is that we have a mask. This is our mask for any color we want because we have black and white. So we have all ones like we have all the components are the same. So anything we do to it will be pretty like similar to what it looks like up here, just with color. So the next thing we're gonna do is we're going to t. You remember this t value? That's what I'm calling my interpolation value for this tutorial, I guess. Oh my God, we're using length again. So nothing happens here. Oh God. Nothing happens here visually, but this is the same thing as distance, literally the same exact thing. Now, don't worry too much about what's going on here. Actually, I'll show you. I could just output what t is doing, but so all we're doing here is just shaping it a bit, and I'll set color to t real quick. Yeah. Oh, so look, we have kind of like this shapened blob of white to black. And this is another mask too, because if you guys look on the example, you see how it gets kind of darker on the edges? Like it's not all uniform. We're going to use this as a mask for that. That's going to be our interpolation value for our previous thing, our previous like radar looking thing. So we're going to not render T, or we'll do that later, but okay, now we need color. Color. So this can be any color. I just chose this is a, you know what? Let me do this on separate lines. So we're gonna say C1 is equal to vec3. Oh, okay. I have like random I have like values that I got here. So actually C1 is gonna be our target value. The other value we're gonna use is just black. So we're gonna use vec3 0. But this value, just you can use whatever, but this is the one that I had on my example. 5, 9. Okay, so that's, did I just, oh my God. So that's a color. Yeah, that's just a color. If we outputted that, you would see just one color on the whole screen, and it would be the green that we have. So that's like a green. And then, oh, so we have this color, but now we want to use that second mask we had, the T mask, to be able to transition between green and black for the edges. So now we're gonna define vec3. This is like our actual color. I'm just using really bad at naming here. But can anybody guess what function we're gonna? Oh, can you guess what function we're gonna use? Mix. Did you say mix? Mix. We're gonna use mix. So yeah, we're gonna literally just mix between the two colors. So I'm gonna mix between 0. So again, that just makes vec3 full of zeros, and then C1. And then what value are we gonna use to interpolate? T. So and then if we output, that's already what? Oh, I'm missing a parentheses, I think. Oh, and then I have to output just color. I just want to show you guys what this looks like. It's just our mask, but it's green now. Wait, oh, that's cool. Okay. So now what? All right, well, we have that other mask. So we've gotten rid of basically one mask. We've used, I mean, we can still use it for other stuff, obviously, but we're not going to. But now we want to use that other mask. So that other mask we have was just called mask. So we have our color, right? And we have 1 and 0 values for our mask, basically. So if we want our color to show up, we want it to be we want it to be what color is. And if we don't want it to be, we want it to be what mask is. That was a bad way of explaining it. But the important part is that mask is a 0 to 1 range, right? So if we multiply color by mask, you'll see, and I output it, you'll see that we have it. It's there. So we took our white and black mask and then just applied that to color. And that's that. Yeah, that's the goal. You guys use all these tools, and we got this pretty cool little radar thing. And there's a lot of other stuff you can make too. Yeah, so that's the mask. That's the power of the mask. Okay, so I think that's pretty much it. If you guys want to do more further exploration, these are some good stuff. I myself, I'm a big Unity person, so I put some Unity stuff there because I know that personally. But this is up here is shader stuff, like particular to like just beginner fundamental stuff. So not it's not super like heavy into like the technology you're using. It's more just the theory and obviously there's coding, but you're not using OpenGL for any of that. There's other stuff for that too, but this is specifically for shader stuff, and this is for Unity people who want to go more into like graphics stuff and also shader stuff.
Can I make a shameless plug?
Yeah.
I also want to throw one more up there. For a hackathon, me and my friends made something related to shaders.
I could pull that up. I think it's a big visible.
Pull it up really quick. I think it's also something. It's basically like Shader Toy, but it has AI in it. So there's also ways to learn.
Just type it in.
With that.
I'm using Firefox, so that'll matter.
It's called VisuWorld.
Is
it blocked?
No, I just Desmos is asking me if I want to save my stuff.
Yeah, so if you want to see some more complex, like super crazy stuff, I actually have no idea how any of this works. I'll be entirely honest, but this is the exact same type of code that was just presented on the bottom left. And you can actually use this to let AI generate it, and then you can tinker around with it and it'll hot reload live just the way it was now. So for example, is your mic on? Did you give it mic permissions? No, it doesn't support speech recognition. You'd have to go on Google Chrome, but
yeah,
if you go to the top right, there's a gallery button.
Oh yeah.
I'd go to the next page.
Is that like this one?
Yeah. So there's a bunch of different graphics paradigms with the fragment shader stuff. I still fully have no idea what all of this is. We just let the AI do it.
AI is pretty helpful.
Examples of what you can do if you wanted to see. I think one more is the tsunami example is my favorite that we ended up generating. This was actually trained on Shader Toy, so very similar. Very similar. Yeah.
That's cool.
The ocean and the tsunami. You could actually see the shaders handling the camera refracting light as it's under the water.
And by the way, there's no geometry in any of these. This is all fragment shaders. I mean, unless you guys defined it, unless the AI defined it in like the fragment shader, which would be weird. But this is all basically just math. It's pretty much all just math.
Yeah, that's it for me though.
Yeah. Okay. So, yeah, and then yeah, these links. Oh my God, it's lagging. I'll probably because we're on that page. I guess we'll link the presentation.
Yeah, we'll make sure that this video gets up on the Nighthacks YouTube channel maybe by the end of the week. And yeah, thank you guys for coming.
Yeah, thank you guys. Oh, sorry, shameless plug from I forgot about this. I slipped this in last second. Shameless plug for my club, Graphics Programming Nights. If you guys want to learn more, we're going to be doing some more graphics stuff, workshops. This is our socials, our link tree, I think. But yeah, if you guys are interested.
Also, if you guys have access to a Nighthacks Blade account and you weren't checked in and would like your Nighthacks points, I could do late check-ins on the front. I saw some people come and say. Thank you guys.